we're given a 3x4 matrix and we're asked to find several properties involving rank and basis and so forth. And first off, I just want to reduce the matrix. And we end up with a matrix leading 1 in the first column, leading 1 in the second column. We'll get, that's a negative 5 over 2, 0, 5, 3, and 0. And I think just by reducing it, we're going to be able to get most of these properties from that. A couple of things to remember. The rank of A is the same thing as the dimension of the column space. All right, so if we want to know the dimension of the column space, the dimension is basically the number of linearly independent vectors that we have. And so basically it's just going to be the number of vectors that we have in a basis. So let's jump down before we determine the rank, and look at the basis for the column space. And if you recall, a basis for the column space can be found just by recognizing that we've got a leading 1 in the first column and a leading 1 in the second column. And so if I jump back to A, that means my first 2 columns are 2 linearly independent vectors. And that is going to give us just a real easy way to find a basis for the column space. And in doing that, the fact that there are 2 means that the rank of A, which again is the dimension of the column space, is going to be 2. So there's an example of a basis. The column space is 2. The dimension of the null space, remember the null space is given by the set of all x such that A times x is equal to 0. And so we just kind of imagine if this matrix were reduced and I have my x vector here set equal to 0. Think about the computations that are going to take place, and we end up with x1 equals x3 minus 5x2, and then x2 is equal to 5 halves x3 minus 3x4, and that looks like a 2 there, but that's intended to be a 4. I'm not sure what I said. And then of course we'd have x3 is free and x4 is free. So all vectors of the form x3 minus 5x4, 5 halves x3 minus 3x4, x3 and x4, and we can kind of see that the basis for the column space, the basis of the null space would be given by 1, 5 halves, 1, 0, representing the components for x3 that we multiply x3 by, and then the components that we multiply x4 by would be negative 5, negative 3, 0, and 1. And, I should have written this down here because this is actually the basis for the null space. Alright, so basis for the null space here. Basis for the column space we've already done, but that gives us that the dimension of the null space is equal to 2. Alright, so dimension of the null space is 2, and the rank is the dimension of the column space that's actually also equal to 2, which gives up or brings us to a property, a theorem that I haven't mentioned, but it's in your lecture guide. the rank of A plus the dimension of the null space of A is equal to n. And sure enough, in this case, the rank of A is 2, the dimension of the null space of 2, and n, meaning the number of columns that we have, is 4. So 2 plus 2 equals 4. So our rank theorem checks out. Just write that up here. Okay. And so that leaves us looking for the basis for the row space. The basis for the row space, it's very similar to the column space. We're just looking for the linearly independent rows. And it helps, you can actually write your row vectors as column vectors, but it's just found by a reduced matrix. Look for the linearly independent rows that we have. So in this case, it would be 1, 0, negative 1, 5, and then 0, 1, negative 5 halves, 3. Okay, let's think about how some of these concepts relate to what we've learned before with the invertible matrix theorem. Remember, the invertible matrix theorem refers to a square matrix where we have a matrix that's row equivalent to the identity. So think of a 3 by 3 matrix that is invertible. It means when we do our row reduction, we're going to get the identity matrix. And let's just go through each one of these. Make sure that they, and understand that they're the same thing. The first thing says, if we have an invertible matrix, then the columns of A form a basis for Rn. And we see that to be true because we know that our standard basis, our standard elementary basis, is indeed the columns of our identity matrix. The column space of A is equal to Rn, and the column space would be all of basically the spanning set of the columns. So think about with these three matrices, we can definitely, or I'm sorry, these three vectors, we can definitely form all of R3, again, because they are the simple basis for R3. The third thing says that the dimension of the column space is equal to n. Again, if our column space is just the three standard basis vectors, then there are three vectors, so that works. The rank is equal to n. All right, and again, the rank is the dimension of the column space, so check. The null space is equal to only the 0 vector. And again, if this were A, and we're multiplying times a vector x equal to 0, because remember that the null space is the solution to ax equals 0. And if this is our A, then the only solution is the 0 vector. And then the dimension of the null space is 0. And that's just a little caveat that we have. When the only vector is the 0 vector, we say that the dimension is equal to 0 rather than 1.